episode of Progress, Potential, and Possibilities, discussions with fascinating people designing a better tomorrow for all of us. I'm your host, Ira Pastor. Welcome, everybody, again to another episode of our show, bringing you another really fascinating guest today, involved in creating a better tomorrow on many different fronts. And our guest today is not just a really cool scientist who's capable of conversing with Nobel laureates as well as the lay public, but he's also an accomplished author and a prolific podcaster on a range of subjects. Today, we have the honor of being joined by Dr. Brian Keating, Chancellor's Distinguished Professor of Physics at the Center for Astrophysics and Space Sciences in the Department of Physics, University of California, San Diego. Dr. Keating is a public speaker, an inventor, and an expert in the study of the universe's oldest light, the cosmic microwave background radiation, using it not just to learn about the origins and evolution of the universe, but ultimately to potentially gain insight into an even bigger picture behind the scenes, that is the multiverse. As mentioned, Dr. Keating is a writer, a podcaster of the Awesome Into the Impossible podcast, and the best-selling author of one of Amazon Editor's best nonfiction books of all time, Losing the Nobel Prize. And his new book, Into the Impossible, Think Like a Nobel Prize Winner, will be out in a couple weeks. Dr. Keating has his bachelor's in physics from Case Western Reserve, his MS and PhD in physics from Brown, his postdoc at Stanford, and his National Science Fellow postdoc from Caltech. Dr. Brian Keating, thanks so much for taking the time to come on the show today.
Thank you, Ira. And just news coming in right now. My mother-in-law would like to present the rebuttal to your introduction. It was too kind. That's what happens when your mother writes it, not your mother-in-law.
There you go. Well, it's great having you here, Brian, today. I'd love to start things off. If you can, from sort of the time you were conceived up until the time you arrived at Case Western, when did you fall in love with physics?
Yeah, for my own personal Big Bang, my parents' Big Bang, rather. I've been in love with physics and astronomy since I was a little kid, since I would notice things like the moon following me wherever I went at night in the car as a young child, wondering why that was, all the way up until when I first looked through a telescope at the moon at age 12, and repeated unknowingly and without actual intention Galileo's discovery of the moon's craters and mountains, et cetera, and then later discovered the planet Jupiter through the same telescope, the rings of Saturn, the phases of Venus, distant galaxies where light had traveled for 3 million years to reach me. This is in the mid-'80s, so this is long before Google existed. I couldn't look up on Wikipedia what I was seeing over the skies of Dobbs Ferry, New York. And it compelled me, because of that lack of easy tools to research, I had to go to the library or wait for the New York Times to come out, and the Sunday edition would have a section about the cosmos. I don't even think they have that anymore. They have horoscopes in most newspapers, but they don't have like what's happening in the heavens. And that was before Amazon and other things, so you couldn't buy books easily. But it forced me to do hard work to learn the basics of astronomy. I just became fascinated in it. But I never thought it would lead to a career. I was like, are they going to pay me to be an astronomer? I mean, would they also pay me to be an ice cream taster, or a wizard, or, a magician, get a lucrative career from that? No. So I didn't think of it as a possible career for many, many years to come after that, but I was always in love with it. And I did it for the purest, amateur means, love of, and that's what I was doing it for. And lo and behold, here I am, a professional astronomer many, many decades later.
Outstanding. I'd like to start off talking about a couple topics that have been core to your research over the years that you talk about in Losing the Nobel Prize. And the first of those, obviously, just the concept of the multiverse. And interesting, in your book, you propose a very elegant model. You borrow from sort of my world of the life sciences, where you talk about a Petriverse, where you posit this plate of nutrient-rich agar, sort of representing this infinite potential of the multiverse, the cosmos. You plate little big bangs of bacteria, which grow, expand exponentially, forming little bacterial universes. Yet these little universes, they'll never meet each other due to various things that we understand about the way bacteria communicate, quorum sensing and electrotaxis and all sorts of other neat sounding things. When you're sitting around thinking and brainstorming about the multiverse nowadays, is this the model that appeals to you the most, or are you into other models as well of thinking about the multiverse?
Yeah. So I should say, in case people aren't familiar, the multiverse is really an extension of what's called the Copernican principle, that just as the Earth is not the only planet in our solar system, the sun is not the only star in our galaxy, the Milky Way is not the only galaxy in our observable universe. Our observable universe might not be the only universe in the so-called multiverse. And so it's kind of an extended. When we were kids, everything that existed was called the universe. And now we've added to it as physicists collectively the potential for an infinite number of worlds, not just a large number, not 9 planets, 10, 8 planets, whatever, but an infinite number of worlds. And in such a universe, the effects that occur downstream are manifold, including impacts on theology and philosophy and all sorts of properties of logic, even probability, statistics. So the stakes could not be higher, in my opinion, and that's why I found it fascinating. Do I believe in the multiverse? This is not something that I think is really consistent with my goals as a scientist, which is to study things for which we have evidence. So in order to have evidence, we have to have a mental model, at least to try to deduce things from the implications of a theory if taken seriously. If you take the theory of the multiverse seriously, you then have to extrapolate mental models. So one of the mental models I've already mentioned, just as we have many planets means that we and many stars, at least the possibility is not forbidden. There might be many universes. So that's one level of analogy. But it's not really that evocative as I think my Petriverse was, in that what we're trying to suppose in cosmology is that the existence of our universe tells you that the conditions are right for the laws of physics to provide allowable life forms like us to evolve, sort of a version of the weak anthropic principle, what's called the weak anthropic principle. But to go deeper, you could say our existence means just the same as it would be to a sentient bacterium. It, and I'm not going to say he or she, but I'll say it, could posit that because I exist, there is potential for other cultures to exist. Mm-hmm. And therefore, the question that next would come to the forefront of that, mind of the bacterium is, how could you observe evidence for this? So we have evidence for planets other than the Earth. We have evidence for stars. We have evidence for galaxies. We have no evidence for other universes. But how could you get evidence? Well, if the evidence is not forbidden, it's said in physics, it's mandatory. In other words, if a process in quantum mechanics is not forbidden, it occurs again and again in some parts of laboratories or the universe itself. So my kind of gestalt there way of thinking was, well, what kind of mechanisms would prevent us from seeing the multiverse? What kind of analogies could be drawn between the non-observation of other universes? And one that came to mind in the Petri dish example are these toxic cultures, which my colleague Herbie Levine, my former colleague here at UCSD, and his colleague in Tel Aviv worked on, kind of this like chemical warfare that you're probably much more knowledgeable about between these cultures. That could be something that prevents a bacterium from learning about another culture, even though they exist. So it would be left just by saying, well, the agar exists, therefore the potential, the laws of our existence are not forbidden. There's potential, but we may never observe it. And so that was the hope of that analogy that I used in that book.
It's a great analogy, and the other part of your research that I wanted to focus on, you've been quite focused on a period of time, some time equal 0 at the point of the Big Bang, or 10 to the negative 34 seconds or so after the Big Bang, when this amazing event called inflation happened, to about 380,000 years after the Big Bang, where the cosmic background radiation is first produced. And in that time frame, after inflation, all sorts of interesting, cool things happen with cool names like baryogenesis and nucleosynthesis, to get to a point where there was something that generated cosmic background radiation that you could see. However, your program was looking for things that were very difficult to see, namely these interesting space-time ripples known as B-mode gravitational waves that, as you know, I read about them, sort of sound like sort of the opposite of gravity, so a gravity that propels as opposed to attracts things. Say a couple of words about inflation and specifically sort of this B-mode gravitational waves that you were hunting down within the CMB.
Yeah. So the dominating paradigm, equivalent in the life sciences for, evolution via natural selection, micro, macro, the dominant paradigm for cosmic structure to evolve and to adapt. Literally, it is evolving under the forces of gravity, not natural selection. There are some that say natural selection does take place in a Darwinian sense in the cosmos, the fecundity of the universe, et cetera. I don't get into that, but in this particular case, for what I study in cosmology, the story of the evolution and origin of the universe, we are missing a great deal of kind of the tools that a biologist might have, in that we do not understand the initial conditions of our system, and it may be in principle impossible to unravel what those initial conditions were. On the other hand, in contradistinction, we understand exquisitely accurate the evolution, the dynamics, the composition, and the behavior of the universe since the origin of the universe. We just don't understand that initial moment. Now you might say, well, you guys understand everything from 13.8 billion years after the formation of the elements, typically called the Big Bang. You understand how the elements formed. You can even say you've replicated some of the physical conditions of the early universe in laboratories on Earth, like the Large Hadron Collider, reaching temperatures of, 1 trillion Kelvin equivalent. But there's a big range, Ira, between 10 to the 12th Kelvin and infinity Kelvin. It's not just like, oh, well, it's a big number. Or equivalently, when we talk about understanding time in the reverse sense, we understand all the way back to a few minutes after the Big Bang, maybe even a few seconds after the Big Bang. But there's a huge gap between that time and zero time on a logarithmic scale. There's infinite amount of intervals. And we want to understand time equals zero. And it's not clear if we can, in the context of ordinary scientific pursuit, understand the origin of time within a framework of science that relies on the changes of that very quantity, i.e. time. How do you study time if you posit that time itself began? And so inflation is best thought about as a mechanism that comes concomitant with the multiverse, because there's no other way to instantiate this quantum field called the inflaton, which then sparks the rapid escalation of the size of the universe and the formation of elements and the eventual seeds of ripples of structure that form in the universe. But there's no necessarily predicate, preceding adopted understanding of the universe. Either it came from nothing, or it might have come, as I've studied on my YouTube channel in several episodes, it may have come from a preceding universe that kind of collapsed, and from which our universe arose like a phoenix. So I think it's fascinating to note that we don't have, we kind of have this exquisite skyscraper, but it's built on a shaky, sandy foundation, maybe like at the beach. And that's unfortunate, but it doesn't stop us from A, conjecturing, and B, trying to learn as much as we can about the superstructure, even if we can never really firmly root it into bedrock below.
So, Brian, you create the Cosmic Microwave Background B-Mode Observing Campaign. It's called BICEP, Background Imaging of Cosmic Extragalactic Polarization. You hang out down at the South Pole for a while. There's the Successor Project. And things, there's some peaks and valleys here. This part of the story is in the book. You talk a lot about it on the internet, you lecture about it. I'm not going to go into sort of the accident and the dust that got in the way. People can read about that story, but I would like to talk about sort of as an outsider to the world of physics. I hang out in the pharmaceutical industry and the life science domain. What happened in this program, I don't see as an outsider as sort of unforgivable. You didn't spend $100 billion and put a space station up there, and you forgot about the oxygen. Or I come from an industry where people waste billions of dollars every year, and they get more money afterwards, and they get promoted for it. Is the world of cosmology about thinking about the multiverse at this level, the experimentalist, as you call yourself, is it really that unforgiving for things like this? Talk about that a bit.
I think it's not, but I don't think that's necessarily a good thing. We've had many examples of discoveries that weren't, and because of the kind of outsized impact that cosmology and physics in general have on our understanding of the universe, I think it's and our place within it, and that naturally people want to talk about. As you asked me about my origin story, people are fascinated with origin stories. How is it possible to look back in time and not, or look out in space and not wonder where did it all come from, as well as every religion and that I know of having something to say about the origin of the universe, in particular Judeo-Christian religions, starting with the origin of the universe, perhaps in the "Let there be light" famous saying. So I think it's endemic in human curiosity to be fascinated by where did we come from. I always ask people, what's your favorite day on the calendar? Usually people say it's my birthday, my anniversary, my kid's birthday. Those are all origin moments. And so there's something deeply ingrained that humans want to know about, because it's the only thing that, in some sense, we can't really witness besides our own death, maybe in some cases. So those endpoints, which is origin of a different phase of life, right? So I think it's natural that humans will be fascinated by our origin, but that comes with a concomitant sense of responsibility, that when we discover something about the physical universe, we should not hype it. We should not turn it into a spectacle. We should not overplay, what we've discovered in order to drum up support, financial, intellectual authority, et cetera. And we should be very skeptical of our own confirmation biases. Mm-hmm. So these are played into in large part by the Nobel Prize. On the other hand, the general public likes it and the media like it. So, for example, for us, we announced that we did discover the inflationary universe, the signature of inflation, the imprimatur of inflation by these particular type of signature of the oldest light in the universe called the cosmic microwave background radiation. And we claim we discovered where it came from. And then that, as I said earlier, comes hand in hand with the multiverse. So you have inflation, you have the multiverse. So we really said we discovered gravitational waves, which had yet to be discovered at that point directly. And we discovered the evidence for inflation, and we discovered evidence for the multiverse. So these are huge things. This obviously appeared on the front page of the New York Times, the San Diego Union Tribune, the best newspaper in the world, and CNN, everywhere. 3 million people watched a viral video from Stanford University, highly produced about it. And yet nobody, even many people, nobody in the lay public, and many people in physics still think that results still stand. I still meet people, oh, you invented bicep, like you guys discovered the origin of the universe, right? And so my problem is that not that the discoveries appear on page 1, but that the retractions appear on page 17 in the weekend edition that nobody reads.
Moving into the new book, Into the Impossible, Think Like a Nobel Prize Winner, you spent time interviewing 9 Nobel Prize winners in physics, and we'll get into a couple of these cases. But about a third of the way through this book, you write a mini chapter called Interstitial, where you focus on introducing the reader to the importance of the scientific method. Talk first about why you wrote this mini chapter.
So I wanted to kind of demystify the scientific method as something that is remote, specialized, practiced by special individuals using special tools, and really say that no, you can basically do this no matter what you do. It's just a way of systematic thinking. It's not like Galileo, who's widely recognized as the first practitioner of it in the modern sense, said, I'm going to apply the scientific method, because there was no scientific method. But the process of simultaneous checks and balances, of auto-defay, of auto-falsification, which we did do quite well, even after we, mistakenly interpreted the origin source of our signal. We were yet very scientifically acted with great scientific integrity in basically retracting by scientific standards what we had discovered or claimed to discover. So this is very important. I think that humans who are not scientists, and contrary to the myth, scientists are all humans for now. But the point being that I wanted people to see that there's no one agreed upon method. So you hear people like, we're the party of science, we follow the science. What does it mean? Because not even scientists have one unique way of getting at it. And I've never started off as I did in ninth grade biology, well, here's the hypothesis, here are the materials, here's, that just doesn't happen. And so we are left with this misapprehension in the general public that it's uniform, there's some perfect, unfailing code. And if you just follow it, out comes knowledge. And that couldn't be further from the truth, as you know. And so I wanted to illuminate for people what it's like to, to have not only the outcome of science, but the very method of science itself. Because I think people use things like the, peer review and all these things. They're all modern inventions, even journals. Peer-reviewed, journal. No, that's been in existence for about 50 years, in its current form. So I think it's overblown, and we do ourselves a disservice as scientists to promulgate the myth that it is done by these unerring, perfectly artificially intelligent, supernatural, preternatural geniuses that never make mistakes.
Gotcha. And if I can quote a small passage at the end of that section, in science, you must not only trust your critics, but accept the fact that you need them. Their participation as adversaries strengthens you and your work, making you anti-fragile. And this was a fascinating line, because one of my favorite books, aside from yours, of course, is the book Anti-Fragile by Nassim Taleb. And he has this fascinating section, you probably read it, something to the effect of, scientists who teach birds how to fly. Where he basically talks about, as important as all this science is and the scientific method, we forget about all the stuff that has gotten here via tinkering. We forget about the Wright brothers bike shop and the fact that Edison, he had horrible learning issues, was a telegraph operator for a long time. And of course, this is leading me into, one of the cases in the new book, that of Rainer Weiss, which you call the tinkerer in this chapter. And one more quote here, make time to tinker and be playful. In doing so, you learn how to problem solve. Just as important, you learn how to fail and how to learn from failure. Talk a little bit about some of the learnings from Dr. Weiss, and a little bit about sort of this issue of tinkering and why it's so important in sort of the scientist's armamentarium.
I think, as it's often said, scientists are very childlike. We have wonder, we have imagination, we have curiosity, we have passion, we're tenacious. And I always joke, we're very much like children. It's true. We're jealous. We're petty. We don't share our toys with other people. So I give a lot of grief to my fellow scientists, but I wanted to highlight, that sometimes you have to get back to your roots and explore, why did you get interested in science to begin with? And I needed that lesson as much as my readers and listeners. And so for me to get reconnected to this 80-plus-year-old, man is still playful, and he still lives by one rubric, which is, if it's not fun, get out of it. That to me, and if you're not learning something new, you got to change the field that you're in, because you're going to stagnate. And there's only so much time. I was inspired to write the book by Freeman Dyson's death. I had some of these interviews, I didn't have others. And I was like, well, he was 89 years old, 90 years old. And he was a great individual, lost the Nobel Prize unfairly, in my opinion, many people's opinion, in the 60s. And yet it was never bitter about it. But the fact that most of these laureates are 80, 70 years old meant that, just unavoidably, unless we cure, you guys cure, death, I think we're going to, unfortunately lose the opportunity to engage with these otherworldly, intellects, or at least people that have an otherworldly impact on society. So from my perspective, I want to engage and show the human side of people like Ray. Ray, I had to cut out a lot of his transcripts. He's so foul-mouthed and he just doesn't care. And I remember, going there to give a colloquium at MIT and just speaking in that, New York accent that I love, and just, it wasn't fit for all audiences, shall we say. So I wanted to kind of inculcate back for myself selfishly, but also for my readers and listeners, how is it to renew your passion at regular intervals and kind of question that. Why did I become a scientist? Because many of these people are so talented, they could do many other professions, not to be glib, but they could do other things that are more lucrative than being, as I am, a public university employee. And yet I keep doing it, and I would do it for free. Don't tell Gavin Newsom, recently reelected governor, got my boss in California. So please don't share that. But I would do it for free, and many scientists would. So always try to connect and resonate with that. And I feel like tinkering best sums up that approach.
Another example that I'd like to say a few words about. In my industry, a thought leader, if they're specialized in breast cancer or autoimmune diseases, they're really specialized in that thing. And most of us that think about the Nobel Prize and the Nobel Prize winners think that they're probably really, really good at one thing. But obviously, Sir Roger Penrose, as you say, most people's work is either deep or broad, but his is both. And here is somebody, got the Nobel quite late in life, work on black holes, but he's equally comfortable in talking about quantum biology and consciousness and a range of other things. Say a few words about Sir Roger, if you would, because I know he's...
Yeah, Sir Roger is an amazing individual. I just spoke at his 90th birthday party in August, a virtual birthday party. And, he is as energetic as ever. I mean, he would have come to the States to have it in person. I think he doesn't really slow down at all. And so for that, intellectually and physically, I'm in awe of him and want to emulate him. On the other hand, he's also very bold and provocative. And I think the larger question is, what makes physicists the people to emulate? Is that just my own bias because I'm a physicist? As you say, biologists are brilliant scientists as well. But I think physicists in particular are kind of generalist in that we typically, sometimes to our detriment, kind of arrogance, it's biology, the famous joke, like a physicist gets into biology, their first, thing is to approximate a cow as a spherical body. And, that's their zoological or biological physics, lesson number one. But I think there is a, kind of nugget of wisdom embedded there, which is that physicists are very general in that we're not the best mathematicians. We're not the best engineers in experimental physics. We're not the best computer programmers or data analysts compared to data scientists or something like that. But we start these fields. We engage in these fields. We study the origin of these fields, and no field in the tree of science is often depicted as having its roots in math or philosophy. And then the first chunk that comes out is physics. And people like Nobel laureate Dirac would say arrogant things like, my equation describes much of physics, all of chemistry, and probably biology too. I don't think cosmologists can really say that. Cosmology touches on every aspect of physics, thermodynamics, quantum mechanics, particle physics, general relativity, special relativity, except biophysics. So, people study aliens. I'm on the advisory board for the Galileo project with Avi Loeb at Harvard. And, we're looking maybe for alien signatures. But besides that, we're not really studying the laws of biology. But aside from that, we have to be communicators, popularizers, translators, and engineers, mathematicians, scientists. So there's no real doubt in my mind where people like Feynman and Einstein, and to lesser extent people like Fermi and others, had these widely discursive intellects and are kind of the image of a scientist. Like if you ask a normal person, who's a good scientist or who's a scientist, they would say Neil deGrasse Tyson, who's an astrophysicist, or Einstein, who is a physicist, it's extraordinaire. So I think these are reasons why physicists are worthy of emulation, and Roger is a particularly apt instantiation of such a character.
Outstanding. So, Brian, we've talked a little bit about losing the Nobel Prize. We talked about some of the cases in Into the Impossible, thinking like a Nobel Prize winner. I'd like to segue now towards your Into the Impossible podcast, which is really one of my favorite shows to listen to. I encourage everyone listening and watching this episode to subscribe to it. I'm going to take on the position of I was your co-host on the show and ask a couple questions about some of the themes that you've gone into that I would like to hear a little bit more about when you interview some of these thought leaders. And the first place I'd like to start is with the theories of everything. You've had various guests on the show that talk about their theories of everything, or unified field theories, which are slightly different. I'm somebody, I need an epilogue in my life, right? I was sad for weeks after Game of Thrones and The Sopranos ended. Brian, tomorrow, if we find out that Garrett Lisi is right, or Eric Weinstein, or Michio Kaku, or Brian Keating, if you have your own theory of everything that we don't know about yet, September 16, 2021, talk about what happens on September 17th. E equals MC squared, got us a lot of stuff in the ensuing decades. Where do we go with the unified field theories and the theories of everything?
Yeah, I think it's very interesting because we have this fascination with them. And I think in part, the reason is because it's kind of Einstein's unfinished symphony or Einstein's last final theorem, these things that captivate in their finality, the kind of memento mori, the realization that life is finite, and that you want to accomplish maybe what Einstein couldn't do or Fermat couldn't do. So for these reasons, things like theories of everything, which hypothesize that there is a fundamental unified description of nature that is both elegant, beautiful, simple, in a physics sense, not mathematically, but elementary, etc., that these exist. And I think, I claim there's no real necessity to mandate that they exist. In other words, it may be a reflection of our bias towards things like beauty and symmetry, parsimony, that have been good guides, but may no longer be. And that the mission of physics to some people is to uncover that. And in so doing, we'll have, as Michio Kaku has been a guest, says, this 1-inch equation that does what Einstein couldn't do, wins a Nobel Prize, and is the God equation. And I think, your kind of prediction or maybe timeline is, needs a couple of zeros on it, because we are quite far away from it. And I think the reason is because what we have now is so successful, and that there's really now we're in this desert where we can't really predict what new inputs we can discover that will help us define the boundary conditions. As I said earlier, the problem with inflation is we don't have the initial conditions. Mm-hmm. In a petri dish, there's a boundary and an initial condition. When you start it, the chemotaxis,
Sure.
This, the reagent. But in the universe, you don't have the initial conditions. And in the particle physics realm of the theories of everything, we don't really have the boundary condition. We don't understand what are the inputs because we don't have new and powerful enough experimental tests to access the ranges of energy, et cetera, that we need to go deeper than we already are at. In other words, all the low-hanging fruit is gone. It's been gone for 50 years, some say. The Higgs was like the last major thing, and to be added to it, and most people assume that it was there. For it to not be there would have been, truly revolutionary. So, and I don't think it's necessarily a bad thing. My sub-project on Into the Impossible and Dr. Brian Keating on YouTube is really what I call the Assayer Project, which is what Galileo's second or third book was called, Il Saggiatore, which meant the assayer, the one who takes a piece of rock and rubs a piece of gold on it, or what's thought to be gold, what's hypothesized to be gold. And depending on what kind of mark is left, he or she can determine if the gold is yea and verily true to the claim. And if it's not, God forbid, the guy's probably going to lose his head. But this is a very valuable analogy, because you're taking something that is not valuable in itself. It's not like a work of theoretical, beauty, these experiments that we're working on, but yet it has the ability to assay and test the true precious nature or lack thereof of these theories. And I think what's missing now, and the reason I'm not sanguine it's going to happen, on the 17th, is that we are so successful as experimentalists, that we've mined a lot of the data on Earth. And so for that reason, we really have to go out into the universe and use the entire cosmos as our laboratory. And that's what my colleagues and I are doing on the Simons Observatory and other projects. So I think it'll be quite some time before we can really even constrain further than we already know now. What are the boundary conditions on a purported theory of everything?
Got it. And connecting to that, I've heard a theme on your show from some of your guests, sort of lamenting the current state of funding of basic physics and the segment. If I was to come up here with whatever, $1 trillion for you, and I'm going to invest it in the Keating Institute of Advanced Physics Thought, whatever. Talk a little bit about what you're going to invest in, looking out.
Yeah, so it would be clear for me, the most interesting thing to do would be to do a truly impossibly deep, but I mean, theoretically possible with that much money. We could make an observatory that could actually go back to the origin of time itself and reveal whether or not general relativity is the core theory of the evolution of the universe. So in order to have a theory of everything, you have to subsume, and as I said, do what Einstein could not do, which is to create this unified theory of light and matter and gravity and space-time. And he wasn't able to do that with all particles in nature. And even he died before any of them were really unified, except for electricity with magnetism. So on the other hand, what we could do with a large enough cosmic microwave background experiment is to build a network of telescopes which would have the capacity to reach what is called the floor of gravitational perturbations. And is that doing so would either reveal one of two things: that inflation took place, in which case we'd understand the spark that ignited at least the hot Big Bang that we observed the aftermath, the shrapnel thereof, or we would reveal that inflation didn't take place and perhaps another form of origin story took place, a cyclical model, a bouncing cosmology. Or thirdly, we reveal that general relativity is wrong at some level. We might see cracks start to appear in general relativity, which, by the way, is so successful that it's in every one of our phones. General relativistic corrections adapt to changing gravitational fields so that your GPS in your phone works accurately. Without general relativity, you do not get to where you're going accurately. So, and despite having general relativity, I often get lost. So that's a little bit frustrating. But you know, for these purposes, I think that would be most direct. Now, I'm obviously biased by being a cosmologist, but nevertheless, I still think it would be the most fascinating thing that's eminently doable with enough resources. Another very fascinating thing that guests have proposed is building solar system-sized particle accelerators. And these wouldn't even cost your $1 trillion from the Pasteur Fund. This would cost much less. So, so for those reasons, these are the types of experiments that I'd be most keen to build. And I think they'd have huge payoffs in order to really reveal if we're barking up the right tree or not.
Right. We've had a little overlap between our shows. Avi Loeb has stopped by here, Jill Tarter from SETI, and you know their work is, you know, you're acutely aware, ultimately posits the existence of advanced extraterrestrial life forms that either can communicate with us in very unique ways or traverse the cosmos. Over the years, I've had the opportunity to talk to some other folks, people like Penny Boston, who used to run NASA's astrobiology group, Zheng Zhao down at DARPA, who, aside from working on artificial intelligence, likes to think about octopus brains and what it's like having 9 little brains as opposed to 1. And then, of course, Mike Levin up at Tufts, who's recently created the Xenobots, these brainless little frog robots that are going to be doing all sorts of interesting things for us, potentially out in the cosmos. As you sit around and brainstorm about, you know, what potentially is out there, you know, in biologic form, what are some of the things you think about?
Yeah, I often think about these as huge questions. You know, other life forms, other intelligent life forms, do they exist? As I mentioned, I am, you know, involved with Avi on his fascinating Galileo project as an external advisor, not an actual scientific contributor. But I think that's, you know, are we alone in the cosmos? The fascinating questions to me are always these chicken or egg questions. How did the universe come from a non-universe, if indeed that happened? How did matter, inanimate matter, become living matter? How did, you know, inorganic matter turn into organic matter? How did the organic matter become conscious, creative, intelligent, technological? These are all huge missing lacunae in our understanding of physical processes, which are in principle understandable. I also like to think about kind of like the next day. You asked me, like, what happens the next day after a theory of everything? I'm quite convinced that if we discovered life on Venus's clouds, as Sarah Seeger and her colleagues and others have spoken about on my show and others, that almost nothing would change. Even if we discovered advanced civilization, and I use, the not counterfactual history, the actual factual history of our species. The fact that I can walk a mile or two from my office and go down to the Pacific Ocean and scoop up a glass of, the Pacific Ocean's finest microbes and plankton and floaters, and maybe get a tiny little sand crab in there. And then also find in there, oil, toxic waste, plastic debris, and, what we're doing to our own planet. It's not a large step to think we'd probably do the same to another planet in some time, on Mars if Elon has his way, and elsewhere if perhaps we do make contact. And then sentient, human beings have been murdered by the millions on Earth. And it's like, are we waiting to see something as amazing as a human being? Would we treat them better than we treated the Cambodians and Tigays and Jews in the hall? No, I don't think there's any reason to suspect we'd be morally moved in any significant way. That's not to diminish the importance of trying to discover them. I'm just always cautious to make too much of the materialist conjecture that this will change everything. And this is, aliens are what we've been waiting for. I think it's a form of wish fulfillment. Like it's going to somehow put into stark contrast the fragility of life, whereas we've known the factual history of humanity since its origin is towards bloodshed and murder and atrocity. And so I'd rather focus on our moral, kind of quandaries on Earth and not look to microbes or little green men as our savior to give us meaning and purpose and take us away from our destructive past. Again, this is all said with extreme enthusiasm for the search for extraterrestrials, putting my time where my mouth is by, at least participating in conversations about this and hopefully advice to the scientific community.
Excellent. Just got a couple more for you here. A couple of weeks ago, you had famous cardiologist, scientist, author Dr. Eric Topol on the show, and you referencing Erwin Schrödinger's "What is Life? The Physical Aspect of the Living Self" in 1944. You asked Dr. Topol what life was. He gave you sort of a fairly standard biologic definition. I'm going to throw that one back at you as a physicist. What is life to you, based on everything you've been studying and what you've gleaned from your origins work? Got any thoughts on what it's all about?
Yeah, I mean, life, certainly some kind of a very complex emergent phenomenon that resists kind of purely simplistic, I would say simplistic materialism, to say, is purely evolved, from chemicals, as Michio Kaku talks about in the God equation, sort of even as a agnostic in his words, or even practicing Presbyterian, I think, he'll say, well, we understand the origin of life because we understand, it's Darwinian evolution. And I think that's very glib. And I pushed back on my conversation with him because I don't think it's at all accepted. And I think, on the other hand, young Earth creationism is anathema to me as well. But I'll talk to people like Eric Topol on one hand, and Max Tegmark on the other hand, and the third hand, I'll talk to Stephen C. Meyer, who is a design, intelligent design advocate. And I can do that because I think that there is ambiguity in all things that are not properly defined. In other words, I can speak very accurately about the lifetime of the neutron and why that's important to the formation of the light elements on the periodic table. And then from there, we could talk about evolution in stars versus in the Big Bang. And then you can talk about formation of carbon and nitrogen, et cetera, et cetera. But I think there are enough gaps, and not to invoke, the God of the gaps, but I think there are gaps that are filled in sometimes too glibly, from pure scientist perspective, like Kaku does with, Darwinian evolution. And in an upcoming book by Brett Weinstein and Heather Hying, who are coming on the show in a week or so, they talk about, basically that genes have a teleology, which I also think is overdoing it. I don't think there's any evidence of purpose manifestation in a gene or even in individual human being. Like I'm not thinking about, I have children. I'm not thinking about, well, what were their 19th great grandchild be like? No, it's not. That's not what I want to have kids so that I can spread my gene. No, that's ridiculous. And so I think there is a little bit too much God of the gaps and science of the gaps. And so I find that to be indicative of an ill-defined problem. In other words, we don't know what life is there are all these things. I'm sure you've read them, Ira. What is it like to be a bat? Sure. Answer, I don't know. I have no clue. By the way, I'm going to write a book called What's It Like to Be Thomas Nagel by author A. Bat. These are all things, hard problem of consciousness. They might not, be amenable. And therefore you start to see ludicrous proposals from people that are otherwise brilliant scientists like Dennett and even, friends that have been on the show, that consciousness is an illusion. Donald Hoffman, that reality doesn't exist, because if reality doesn't exist, then you don't have to explain consciousness. Consciousness doesn't exist, then you don't have to explain how did consciousness arise from non-conscious inorganic or organic matter. So these are all ill-defined things. I find them fascinating, delightful, delicious. They may not be part of the traditional quote scientific method that I railed against having a single definition, but nevertheless amenable in the time that I have to devote to them. They may not be as crackable a nut as I like to work on, and yet that doesn't stop me from wildly speculating about them. But I just like to give equal amounts of grief, as I do to scientists and non-scientists, to proponents of that this is a soluble problem versus people that say it had to be God. So I find it vexing and provocative, and not maybe amenable to solution, but nevertheless worthy of attention by serious intellectuals.
Me too. Last one, just and then I'll hear your kids coming home, so I'll let you go to them. There is a handful of cosmologists out there that, aside from thinking of the multiverse like you do, also spend a little time thinking about what the cosmos may itself be thinking about. Folks like Vitaly Venturin at University of Minnesota, who posits, there's a lot of real unique complexity out there in all those galaxies and all those stars and all the fields that exist between them, looking a lot like neural networks and so forth. Provocative, interesting. Give me a couple seconds while I have you about once again the consciousness of the universe.
Yeah, I think a lot is overdone about that. You can have these neural network maps and the number of stars in the universe, the same as the number of neurons, connections. The connectome can be much bigger, and therefore, I say, well, literally, when you get a piece of cauliflower, it looks like a brain. It has fractal structure, maybe self similarity. Does that mean it's a hydrodynamical cosmic simulation? No. So there is a lot, and that reflects back to what we talked about earlier, which is the desire for human beings to see patterns, inflections, and sort of nuance where there might not be any. It might be coincidence. Again, there's it's often said that, the study of, comic books are not very scientific or worthy of intellectual pursuits or scholasticism, but the study of the history of comic books is. And so I think studying where do these things come from is worthy of being is worthy of scientific attention, but making too much of superficial things leads to a lot of woo-woo. The universe is conscious and everything is conscious. And then there are people that take that seriously, that'll believe in what's called panpsychism, that electrons have consciousness. And I think that's, sort of ludicrous because no one behaves that way. I've only talked to met one person so far that believes that we have no free will, but acts on it. In other words, people will say things like free will is an illusion, and then they'll order, pizza for lunch instead of sushi. And then you ask, well, why'd you do it? And they're not going to say because of the Big Bang. I think it's ridiculous. I did meet one person, and I thought that he should seek psychological counseling, that he believes that he has no free will, because I think there's a propensity for those people to be sociopaths. But anyway, this is all, delicious, delightful speculation, which I engage upon as well. And I just want to thank you for hosting me on the show. And I've been a fan, and you're so dogged in your pursuit, and you're great guests. It was delightful for me to make an appearance on the Triple P. Quadruple P.
It was great. It was great having you, Brian. Once again, for everybody that's going to be listening to this episode or watching on the YouTube channel, you've been listening to Dr. Brian Keating, Chancellor's Distinguished Professor of Physics, Center for Astrophysics and Space Sciences, Department of Physics, University of California, San Diego. Pick up a copy of Losing the Nobel Prize. Check out in a couple weeks Into the Impossible, Think Like a Nobel Prize Winner, which will be available through all sources. And also, if you haven't subscribed, subscribe to the Into the Impossible podcast. Brian, thanks so much for taking the time out of your schedule to talk to us. Thanks for everything that you've been doing, as we say on our show. Thanks to helping create the better tomorrow for all of us through your work. Very, very impressive story.
Ira is a delight. I really enjoyed it.